Today we're going to do state estimation part 3, which is nonlinear discrete time Kalman filters. They are nonlinear because the dynamics is just some function rather than just matrix multiplies, and same with the measurement h. But today we will, when we compare measurement errors, measurement residuals, we'll just be subtracting them, so this part's still linear. And then when we do an update, we'll just be adding into the update. So that part's still linear. Later we'll talk about when these two functions are also nonlinear, which is what you need for things like dealing with quaternions. Okay. And in our state estimator for DARPA Robotics Challenge, that's where these things are nonlinear, is with orientation, dealing with quaternions. For everything else, we just use the summations. But these functions are nonlinear for like center of mass estimation, center of mass velocity estimation. Okay, so the way this goes is you have your input u. The red part here is the true dynamics of the system. So you have your input u and some noise w and your state vector x. And so your next state is going to be a function of your current state, your input, and your process noise. And then now go through a delay to get your previous state. Then your measurements, your sensors, will be some function of your current state and some measurement noise v, and that will give you your measurement vector. So in the Kalman filter, you simulate that. That's all the blue stuff, which parallels all the red stuff. So you have your dynamics, f. But instead of knowing the true state, you only have an estimate of it, which is where these hats come in. All the hats are estimates. So your estimate, you know what u is because you're commanding it, but you don't know what w is because that's a disturbance you don't know about. Okay? So then that will produce the next step, state. Notice there's a little minus here and there's a little plus here. So this is the state estimate after you do the simulation of the forward dynamics. So it's like your a priori state before there's some update, and this is your a posterior state after the update. Okay. So you take this state, go through your sensor dynamics to figure out what you would expect your sensor readings to be. Compare the two to get a residual on your sensor readings. Multiply that through by some k-matrix and use that to update your state by adding it to your a priori state to get your posterior state, and then your delay block. Okay, so it's very similar to what we saw before with the linear Kalman filter, except that these are nonlinear functions rather than just linear matrices. And so what you do is you linearize them to make it be equivalent to the linear system, and then everything that held for the linear system holds for the nonlinear one. So all of this just in equation form is you have your actual dynamics, which is your f function, and you have your actual measurement, which is h, your simulated model dynamics. So again, in doing the Kalman filter, you assume that you know these functions exactly, that you know f exactly and you know h exactly. The things you don't know are the state and the disturbance, or that disturbance. Okay, so your simulated model, same f, but now instead of being on your true state, it's on your estimated state. Your input, which you do know, you don't know w. Estimated measurement, same h, but it's on your estimated state before the update, and assuming zero sensor noise.
You still assume like zero mean white noise?
Yes. Yep. 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 V and W, you're still assuming zero mean white noise. And if it's not zero mean, then you subtract off the mean. And if it's not white noise, well, you just pretend it is. Okay, and then your update step. The next state estimate is going to be, well, the posterior is going to be the a priori plus k times your residuals, where your residuals are just the difference in your actual measurement minus what you think that measurements should be. Okay? And what we're interested in here is this estimation error. So we write E sub n plus 1 with a plus to be what the state is, state x n plus 1 minus the estimated x n plus 1 plus, so that's this guy. And then with the minus, that's comparing, so subtracting these two states is the error plus, subtracting these two states is the error minus. Okay. So in code, what you do is you have your input u, so you compute this function to find what this guy is. Then you use this function to figure out what these guys are. You're measuring these, so you subtract these to get this. Then you figure out what your K matrix is, and that we'll be talking about later, how to figure out what to use for K. But that will be a function of the linearization of these guys. Multiply that through to get your update, add it to that guy, and now you got your next state estimate. And the delta t's are just the time step happens. All right, any questions on how all this works? Okay.
Is there any method for this that doesn't rely on linearization?
There probably are. In the same way that there's nonlinear control systems, there's also nonlinear observers. So with, if you want to control something around a fixed point, you can linearize it about the fixed point and then use a linear control system, or you can just use a nonlinear control system.
Okay.
Yeah.
They're
First-
quite limited.
Yeah, there's only so much that is known how to do. So when you stick with linear control systems and linear estimators, pretty much all the theory has been figured out, and it's all rock solid.
Okay.
As soon as you get to really hard nonlinearities, some things it's just impossible to do anything, like pure time delays. Just can't do anything about it. Yeah.
So like when you're implementing this in like in the BRC when everything's going on in Gazebo, where both your actual dynamics are also just simulated dynamics.
Well, no, this is a real robot here. Well, sure. In
But, like,
Gazebo, this is your simulation in Gazebo.
Yeah, but you're also
and then you're
trying to
simulating
copy
it
the
in
simulation,
parallel.
but so like
Yeah.
you could get really close
Well,
in
right,
simulation.
and with the Virtual Robotics Challenge, we knew almost exactly the real dynamics.
Exactly.
So we could probably even not have much feedback and get pretty good estimates
Right.
for like a second
Okay.
or so.
But if
But they're gonna, if they diverge a little bit, then they'll start flying away from each other.
Mhm.
So that's why you still need, even because of like numerical round off or whatever, you still need some feedback.
Okay, but like just by the nature of it being a simulation, you're going to be able to get like way better estimates than when dealing with a real robot.
Yeah.
Okay.
Didn't Gazebo also throw in the W term though? Or,
Yeah.
no?
Oh, okay.
I mean, we knew exactly the dynamics.
Right.
Yeah.
So, but then that's in simulation. Basically, you're just trying to get W and V. Like that's your only real. Or
We should
theoretically-
have added sensor noise, but we didn't. I mean, there's
Yeah.
a tiny bit that was added. And we should have added disturbances by pushing the robot around
Mhm.
or having unknown terrain, which in sense we did a little bit because the LiDAR wasn't perfect.
Yep.
So there is a little bit of
Okay.
Okay, so what I'm going to do next on the other board is show that if you compute the error dynamics, the next step error dynamics, and linearize it, that you get the same exact error dynamics as you do with the linear Kalman filter, meaning that you can use the same tools to compute K matrices and all the results hold, as long as the linearization is close to the actual dynamics. So that's this board over here. Okay, and I wrote it all out today instead of writing it out, so you don't have to watch me make mistakes. There may be a mistake here or there on this guy, but I don't think so. I checked it a few times. But anyway, your error dynamics. So what we really want to know is what is the error after we've done everything. So after we've done the forward dynamics, done our updates, and got to this guy here, this state here, how does that state compare to what we think it is? So that error between these two, and how does it evolve over time? So that's xn plus 1 minus x hat n plus 1 plus, which is just the f function given the regular dynamics. So this is the plant given the true state, the input, and the true noise, minus, so x hat n plus 1 is through the dynamics plus the update. So that's, this is the forward step dynamics, f given your previous state estimate, the input you know, and 0 because you don't know what w is, plus k times your measurement residuals. Okay, so the trick we're going to do here is make these f's look really similar except for some deltas, so that we can then use the first derivative to approximate what the function is. Okay. So we know what x hat is, so we keep this guy here. We don't know what this guy is, so let's make him in terms of this guy so that the difference is a little bit small. So x, the true state, is going to be the estimated state plus the error in the state. Okay? And you need to make sure that you have en plus and xn plus. So that's what that equals. And so now you can see that with f we have something that's exactly the same plus some delta, and this delta is typically is expected to be 0, so we can linearize about that delta. And u's are the same, and w is expected to be 0 mean with some 0 mean white noise, so we can linearize about 0 there, and that's how we linearize it. So it's kind of stating that again. If we look at what f given x hat n plus some delta x and u and some w, that's going to approximately be f evaluated at just at x, u, and 0, plus the derivative of f with respect to its first parameter, x, that evaluated when x equals xn hat plus, when u equals 0, and when w equals, or u equals u, w equals 0, times this delta x, right? Plus the derivative of f with respect to the third input, w, evaluated at the same point, xn hat plus u 0, times the w, w is just expected to be small, plus some higher order terms, and those are what we can ignore when we're linearizing. And let's just call this matrix here f, and this matrix here w, this part here, and so we large w's times small w. Yep.
I'm trying to follow and getting confused on which terms are.
Yep.
So the large W is based on the error in the real world error. Yeah.
So f is just the derivative of, capital F is the derivative of the function little f with respect to x, evaluated at these 3 points. See, there's 3 inputs.
Yeah.
So the inputs are those 3. And
What's F?
F is the dynamics,
Okay.
the forward dynamic equation. So it's f is a function of x, u, and w.
Okay, and U is your control input, W is error, X is your current state.
Does that make sense?
Yeah.
Just in general, if you have some function p of inputs a, b, and c, and you want to linearize that about a naught, b naught, and c naught, then you'd say that p of a naught plus delta a, comma b naught plus delta b, comma c naught plus delta c is approximately equal to that function with respect to the first variable a
Let's see.
evaluated at A naught, D naught, C naught
But first,
times delta A. Sorry, P of A naught, B naught, C naught plus. It's just there's just three things that in the function.
So it's
you
a
got
Taylor
three
expansion.
It's just a
variables in the
Taylor
function.
expansion, right?
Yeah, it's just a Taylor expansion. We're using just the first order terms.
Okay.
Graphically, if you've got some function f of, let's just look at one variable, f of x, and you want to linearize it about x naught, and you have some delta x. The estimated value at delta x is just going to be the value here, so f at x naught plus the derivative, so that's df over dx evaluated at x naught, so the derivative at x naught
Okay.
times delta x, which will give you about this point.
So we're assuming that whatever that function is, it's a line based on what x it was in the last step.
Locally, it's a line. Yep. So if you zoom in, into there, zoom into any little region, it's just going to look like a line. And so the value here is just going to be the value here plus the slope times the delta.
and how did we end up with the function f that's a function of x hat plus delta x? How do we get the delta x?
Well, the way we got it down here was to notice that x sub n is x hat n plus the error.
Yep.
So this is our delta now. We're just saying let's linearize about this point. So that's the point we're picking to linearize about,
Yep.
and then this is our delta.
Yep.
So here I just said generally, yeah. So just really substitute e sub n, en in there,
Yep.
and then en comes there.
And the f, why is the w still in there?
Let's do that. So delta x is actually plus. And then w is just a small delta too because it's assumed to be 0.
Times w, so times 0.
Well, this is a non-zero matrix, and then this is just whatever w happens to be. Yeah, those don't cancel out because those are your first order terms. You keep those.
Yeah, but I
then
mean,
there'd be something times w
isn't
squared.
w assumed to be 0 mean? So
Yes, but it's not 0. Okay, so then you have those f's and w's, and then to just simplify this then, so en plus 1 plus is approximately f times en plus, f times en plus big W times little w minus k times yn plus 1, that just carried down. Okay. So now we need to figure out what yn plus 1 is. So it's just a subtraction of the actual measurement minus the estimated measurement, which is your h function times your state and your noise, sensor noise. So this is a true measurement dynamics minus h times your estimated state, and your estimated noise is 0 because there's nothing else you can do. You don't know what it is. So this is your estimated measurement. Okay. And so we do the same trick as up here. We figure out how to make this term look the same as this term so that we can linearize about it. So xn plus 1 is the same as x hat n plus 1 minus plus en plus 1 minus. See, we're up, whereas before we were looking at xn, so that was, we used en plus. Here we're looking at xn plus 1, so we use en plus 1 minus. Okay, because that's, take that, add that, and you get that. That make sense? Okay. And so now we have this term, so same as before, if we look at linearizing the h function, we have x hat n plus 1 minus plus some delta x. and some v, it's actually delta, it's a small number. Both these numbers are near 0, we assume. So that's going to be approximately h evaluated at that point in v equals 0, plus the derivative of h with respect to its first term x evaluated at here. Evaluated at x equals x hat n plus 1 minus and v equals 0. Because that's what that and that is. Times delta x plus the derivative of h with respect to the second term v evaluated at x equals x hat n plus 1 minus v equals 0 times little v. And same as up here, we call this matrix H, and we call this matrix V, large V, so that we get yn plus 1 is approximately because these guys will now subtract off, right? So both of these, this term here will have that in it, this term here will have that in it, those two subtract off, and then this doesn't have any nonlinear terms because these are 0 deltas, and so you just get just that part for yn plus 1 is that. That makes sense? Okay. So then you plug yn plus 1 back up into here, and you get oh, sorry. So now you have what yn plus 1 is. You'd want to plug it back in there, but we still have this en plus 1 minus, and we need in the end for everything to be pluses. We want to know what the error is after the update, not before the update. That's what we want in the error dynamics. So now we need to evaluate that part. So en plus 1 minus is just the difference between the true state minus the estimated state before the update, so the minus part. So since it's before the update, it's just a subtraction in the f's. You don't have the plus ky here. You just have f of the true dynamics minus the estimated dynamics. And so same trick. We say xn is x hat n plus plus en plus.
It's exactly the same function, but then without the feedback, right?
Exactly. Yep. X hat. Yep. So we're going to get the same f, which is approximately f times en plus w times w. Yeah. Okay. So then you plug that into yn plus 1 to get that yn plus 1 is approximately h times f times en plus h times big W times little w plus big V times little v. And then finally plug that y into back up here for the next state error next error dynamics. So that, and then throw that back in and rearrange terms so that you get en plus 1 is going to be all this matrix stuff times en plus this matrix stuff times w times big W little w minus k times big V little v. And if you recall from last lecture with the linear Kalman filter, you get exactly this equation too. We didn't have the w and the v, we just had the little w and the little v. But what you can just do is say that, define some new noise terms that are just this matrix times that or that matrix times that, and figure out what the covariances are for those, and then everything else holds the same. So the error dynamics are the same, meaning that the same ways you could choose k for the linear Kalman filter can be used to choose it for the nonlinear Kalman filter. What you need to do, though, where the difficulty lies, is computing these f and h matrices and w and v, which are these partial derivatives. But as long as you can do that, then it's all the same. And as long as the linearization of these functions f and h are close to the actual functions, then it should all just work fine. Any questions? Okay, so next what we will do in the next lecture is, instead of having these be summation blocks where you're just finding the residuals by subtracting, we'll make these guys nonlinear also, which comes into play for things like comparing quaternions. You don't just subtract two quaternions to see what the residual is. You actually essentially divide them, and then you don't just add a quaternion to update it. You actually multiply it, and you will see that these guys need to be kind of duals of each other. If you're subtracting here, you're adding there. If you're multiplying, if you're dividing here, you're multiplying there. So there'll be some constraints on what you can put there and there. They kind of have to have some sort of matching, and then it'll also it'll be interesting how the error is actually defined. So this this function here kind of defines what the error is. Since this is an addition, that kind of means that the error ends up being this minus that. Whereas if this is a multiplication, then the error will be that divided by that divided by that. So, which we will do next.